Have you ever just looked around and noticed the patterns in nature? I mean, they're everywhere you look. Well, it turns out there's this hidden mathematical language, almost like a secret code for the universe that describes all of that beautiful complexity.
Okay, just take a look at this. This is a Romanesco broccoli, and it's the perfect place to start. I mean, those mesmerizing spirals, the repeating shapes, it almost looks like it was designed, right? Almost too perfect to be natural. But it is.
And that gets you thinking, what in the world does this crazy-looking vegetable have in common with a jagged bolt of lightning, or the rugged shape of a coastline, or, get this, the branching network of blood vessels inside your own body? On the surface, they seem completely unrelated, but believe it or not, they all share the same fundamental secret.
To crack that secret, we have to look at how we've always tried to measure the world. For centuries, we had Euclidean geometry, perfect lines, squares, circles. And hey, it's great if you're building a house or a wheel. But nature isn't smooth. It's rough. It's messy. Clouds aren't perfect spheres, mountains aren't perfect cones, and lightning definitely does not travel in a straight line. So we needed a new kind of geometry, a new language that could actually describe the rough and chaotic shapes of the real world. And in the 20th century, one mathematician finally came along and gave it a name.
That mathematician was Benoit Mandelbrot, and this is how he described the field he would pioneer. You've got to love this description. Beautiful, damn hard, increasingly useful. Just got to appreciate the honesty there.
In his groundbreaking 1975 book, The Fractal Geometry of Nature, Mandelbrot officially coined the term fractal. And here's the really crucial part. He was one of the very first people to use the power of computers to actually see these incredibly complex shapes, to visualize them.
Okay, so what is a fractal? Well, the name itself comes from the Latin word fractus, which means broken. And Mandelbrot's own definition really sums it up perfectly. It's a shape where, if you break it into parts, each one of those parts looks like a smaller, shrunken-down copy of the whole thing.
And that property right there, that is the magic key to understanding all of this. It's called self-similarity. All it means is that the same simple pattern repeats itself over and over again at smaller and smaller scales.
And once you know what you're looking for, you see this absolutely everywhere. Go back to that Romanesco, snap off one little floret, and boom, it looks just like a tiny version of the whole head. Look at a fern. Each little leaflet mirrors the shape of the whole frond. The tiny twigs on a tree branch out in the exact same way as the big branches. And of course, snowflakes. They're the classic example, with those delicate arms that have smaller branches repeating the same pattern. Now, here's a quick but important distinction. A purely mathematical fractal is perfect. It repeats its pattern forever. If you could zoom in infinitely, you'd just keep seeing the same shape. In nature, obviously, that's not possible. A tree's pattern stops once you get down to the cellular level. So, natural fractals are approximate, but the underlying principle is exactly the same.
This all leads us to this fascinating problem that really gets to the heart of why we needed this new math. It's called the coastline paradox, and it starts with a simple-sounding question. How long is the coastline of Britain? The answer is a total mind-bender. It depends on how you measure it.
Seriously, think about it. If you use a huge 100-kilometer ruler, you're just getting the major curves, right? You're missing the details. But if you switch to a 10-kilometer ruler, you start capturing all these smaller bays and inlets, and the total length gets longer. Now, imagine using a 1-meter ruler to measure around every single rock. The smaller your measuring stick gets, the more detail you find, and the longer the coastline becomes. It's like it's stretching out toward infinity. So how do you solve this paradox? With a new way of measuring. The coastline of Britain has a fractal dimension of about 1.25. So, what on earth does that mean? Well, a straight line has a dimension of exactly 1. A flat square has a dimension of 2. This coastline is way wigglier than a simple line, but it doesn't quite fill up a flat surface. It exists in a fraction of a dimension. Wild, right?
And that's really the key takeaway here. Fractal geometry gives us a number, a precise mathematical tool to finally measure something as abstract as roughness or complexity.
Okay, so fractals describe nature, but it does not stop there. This once obscure field of math is now being used in some truly incredible ways, shaping everything from the medicine we use to the movies we watch.
First off, we use fractals to model our world with incredible accuracy.
We can describe the ruggedness of mountain ranges, the branching of river networks, the way clouds form, the chaotic path of lightning, and even the large-scale distribution of galaxies across the entire universe.
And that understanding, it powers innovation. In medicine, doctors can analyze the fractal patterns of blood vessel growth to help detect cancer. The antenna in your phone, it's probably a fractal design, which lets it pick up lots of different signals. In computer graphics, artists use fractals to generate those breathtakingly realistic landscapes you see in movies like Frozen 2. It's even used to design stronger materials and model how cities grow.
And this is maybe the most famous fractal of all, the Mandelbrot set. It's a picture of a surprisingly simple equation, just repeated over and over. Every single swirl and filament you see here contains smaller, nearly identical copies of the entire shape. It's the perfect illustration of how infinite mind-boggling complexity can emerge from a very, very simple rule.
So, what does this all mean? Beyond the pretty pictures and the useful tech, fractals offer us a really profound new way of seeing the universe itself.
They show us that underneath all the apparent chaos and randomness of nature, there's a hidden order. There's an underlying principle of efficiency that governs how things grow and take shape, from the smallest leaf all the way up to the largest cosmic structures. It's like a universal building block.
Benoit Mandelbrot himself put it best. In these repeating patterns, which seem like they could go on forever, we get a little glimpse of something truly profound. He said, a fractal is a way of seeing infinity. And that leaves us with one final, incredible thought. If the universe is built on these elegant, repeating, and scalable rules, the same basic logic that forms a snowflake, a tree, and a galaxy, it just makes you wonder, what other simple, fundamental truths are hiding in plain sight, just waiting for us to find the right way to look?